chaps, shall we make a start? Apparently you've got a big walk to Congregation Hall for your next lecture, so I'll try and finish a little early so you can get there in good time. So I've started off with a question. So we've got 3 drugs here, or 3 drugs or biologically active molecules. And have a little go. I'm going to give you a minute to think about what you would do. Draw these structures as you would expect them to appear at physiological pH. So this is something, can you predict which bits are going to be protonated and deprotonated? So I'll give you a couple of minutes and then we'll go through that answer.
Let's just go really right.
Alright guys, I think that's enough time to cause a little bit of confusion for you all. So I'll just run through the answers. So the easiest functional group to work out whether it's going to be charged or not is carboxylic acid. If you can identify carboxylic acid in a molecule at physiological pH, all carboxylic acids are always going to be protonated. So this compound here, it's got a carboxylic acid. So that would be O minus, not OH. So that would be negatively charged at physiological pH. First one was a bit of a trick question. So none of these functional groups would be charged at physiological pH. So there's a bit of a temptation to maybe protonate the pyridine because it's basic, but it's not basic enough to pick up a proton at physiological pH. The pKa of pyridine is about 6 or so. So because that's far less than physiological pH, which is pH 7.4, that's not going to be, the majority of that is not going to be protonated. So what we're actually looking for is we're looking for acids and bases. So we've identified the acids. Now we're trying to work out where are the bases. So these are the ones that are going to pick up a proton and be protonated. So this nitrogen, as we've said, for pyridine, although it's basic, it's not an aliphatic amine because it's aromatic. So that's going to not be protonated. Here we have an amide, and that lone pair is delocalized in with this carbonyl. So that's not basic either. With this compound here, we have another amide. So again, that lone pair is going to be delocalized in here. So that's not basic. But we do have an aliphatic amine here. So this nitrogen, the lone pair cannot be delocalized anywhere. There's nowhere else for it to go. There's no double bonds nearby that you can draw any resonance species. So that nitrogen will be protonated. So you draw a bond on a hydrogen and then a positive charge there to show that that has picked up a proton. So that's what we mean by structures that you expect to see in the physiological pH. If anybody's got any questions on those, do say so now. If not, then yeah. Do you have a question?
Yeah. So,
what about the nitrogen? This one. Why it's basic? So the lone pair on this nitrogen here is available. So it's not delocalized. There are no double bonds nearby. There's no carbonyl nearby. You can't draw any resonance arrows for it. So therefore it's available. So that's why that nitrogen is basic. So for this one, the lone pairs can be donated into here, and you can get resonance because that's an amide. Same here, and then this is an aromatic amine. So they have a lower pKa of the conjugate acid. So basically, if there's any double bonds nearby, then you should be thinking probably not. Okay. So if it's single bond, double bond, then you can get resonance. If it's connected by a double bond, again, you should be thinking probably not. Okay. So what we're going to cover today is hydrolysis. And what I expect you to be able to do is draw curly arrow mechanisms to show hydrolysis with esters, so ester functional groups and amide functional groups. So you need to be able to identify esters and amides within molecules to be able to actually apply that mechanism. I'd expect you to be able to explain why esters are more prone to hydrolysis than amides, and we'll go through that. And that's a very, very common question. But if amides were prone to hydrolysis, we wouldn't be able to exist, because all of our proteins are made up of amide bonds, our nucleic acids are made up of amide bonds, and likewise, in a similar fashion, we actually use the fact that esters can hydrolyse quite predictably to our advantage in drug design. We will go through some other functional groups that can hydrolyse, so acid derivatives, but the principles behind the mechanisms are the same. The ability of them to go through hydrolysis will depend on what type of group they've got attached to that carbonyl. And then we'll have a look at some applications in the drug discovery industry, and I'd expect you to be able to remember some of those applications, to be able to recall those. So why is hydrolysis of carbonyls important? Well, the main thing is that these are a very, very clear point where drugs will be able to be degraded. And it might be through metabolism, and that then leads to excretion of that compound, or it could be that we have introduced an ester group to make it easier to get that drug into the body and where it needs to be. And then it gets hydrolyzed in situ to reveal the functional group that is required in that drug target. So when drug molecules get metabolized, this is what we mean by inactivated medicine. So if a drug is hydrolyzed as part of the metabolism process, sometimes that functional group can be ruined, so it no longer binds in the same way. And sometimes that can give rise to decomposition products which are toxic. So we'll go through some examples of that towards the end of the lecture. So the reactivity of the carbonyl group, there are two different types of mechanism that happen with a carbonyl. So this is our carbonyl group here. We've got the oxygen, which is delta negative, and we also have the carbon, which is electropositive, so delta positive. And you can have a nucleophile attack here, or you can have electrophilic addition, where the electrons from the carbonyl attack an electrophile. So here's the nucleophilic addition, and that gives you this product here. And then electrophilic addition is when you use the lone pair. So this is acting as the nucleophile, and then that will interact with an electrophile to give you this. So sometimes you can activate a carbonyl with a proton. So under acidic conditions, this will actually happen quite readily, and then that actually then activates the carbonyl for attack here. So you might have electrophilic addition followed by nucleophilic addition. So when this happens here, this is very, very electrophilic because you've actually made this more electropositive by having this electrophile on here, by making this positive. So if you attack here, then these electrons would then neutralise this charge. So that's then very attractive for a nucleophile, and that then makes those reaction products very stable. So when we look at a carbonyl, the carbonyl exists in two resonance forms, so we can draw those using these arrows. Note the resonance arrows are double-headed. So these is essentially the two different forms that a carbonyl can exist in. So you've got your negative charge that can then go back and then relieve the positive charge on that carbon, and then that's produced by these electrons moving onto here. So remember, the movement of electrons depicted by an arrow means the movement of two electrons. So that's why we show this as a delta negative and a delta positive, because it exists in both these forms, and although it is possible to have a formal charge on the oxygen and a formal charge on the carbon, this is probably the best way of depicting it. So there are two different things that you can have happen at a carbonyl. You can have a substitution, or you can have an addition. So each goes via a nucleophile attacking the electropositive carbon. So here's your nucleophile, here's your electrophile. So your nucleophile attacks here, so negative to the electropositive carbon. These electrons from this bond break, and then they go up onto the oxygen. That gives you this intermediate species. Then there are two options. So if this negative charge can pick up a positive charge species, like a proton, for example this, that will give you what's known as the addition product, to add something to that carbonyl. But the other option is that if X here is a good leaving group, so it's quite happy to be on its own, so if you break this bond here, it will be relatively happy on its own and stable, you can get a substitution. So then what happens there is the electrons come back down and then kick that off. So this will depend on whether you get an addition or whether you get a substitution, will depend on what types of species you have around this. So if X is a really good leaving group, then you'll get substitution. But if it's not, then you might get the addition product if there's a proton present. So when you draw the mechanisms for doing this addition-elimination type reaction, always draw from the nucleophile to underneath the carbonyl and then up here, just like this. This is the perfect way to draw it. And then these electrons come back down and then kick that off. So this is the correct way to draw addition-elimination. Now what you don't want to do is to draw your nucleophile coming in from the side and then kicking that off, because we always put the electrons up on the oxygen and make them come back down before it kicks off this leaving group. It never just goes in and then kicks that off. So that's a type of substitution that we'll learn about in second year called SN2, and that never occurs at a double bond. So you're never going to see that type of this type of mechanism where there's a double bond. Okay, and the reason being is because the orbital overlap for that is not appropriate, but you will do more about that next year. So you don't draw it out like this. Always onto the carbon, and then these electrons go off onto the oxygen and then go from there. The other thing that you don't want to do is have the leaving group leave first to give you this electropositive species. This is just not the way that mechanism is going to go. So again, this type of mechanism is another type of substitution that again doesn't typically happen at carbons that have a double bond. But you'll learn more about these two other types of substitutions next year. So we'll always draw it like this one. And I mentioned before there are good leaving groups, and there are leaving groups that aren't very good. So, for example, I think the easiest one to think about is when you think about chloride, Cl-, quite happy seeing that on its own. So, like for example, when you've got HCl as an acid, you're quite happy to see, or you're quite familiar with seeing H+ and Cl-. That's because the chloride is very happy, it's picked up its extra electron that it needs, and it's almost like a noble gas. That's quite a familiar thing to be kind of happy with, and that's the reason why Cl is a very good leaving group, because, because when that bond breaks and that chlorine takes those extra electrons, it's very stable, it's very happy, and because it's stable, it makes it a really good leaving group. So some of these other functional groups that I've highlighted in red are also relatively good leaving groups, and for similar reasons, because they can acquire a proton, or they can be stabilised by resonance. This group here can, once it leaves, so if you break this bond here, then this would become negatively charged, and that can be delocalised across here. So that's what makes these good leaving groups, that they're stable. Now, poor leaving groups are groups that don't have that ability. They don't have anything that can make them stable. So, for example, if we have an aldehyde here, if we have these electrons move on to here, that would be H-. Now, H- is you would only see a H- form in very, very exceptional circumstances in organometallic reagents. They're not stable at all. You have to really force H- to form. If you think back, you're usually used to seeing H+. H+, happy. H-, very, very reactive and not very stable, so it's not a very good leaving group. And similarly here, with a CH3, so if this is a ketone, and you've just got a methyl group, this would be leaving as CH3-, and carbons tend not to like to have negative charges on them, or really positive charges, to be honest. So this is what makes them very poor leaving groups. So the two main hydrolysis mechanisms that you need to know are the ones for the amides and the esters. And essentially what's happening here is in this carbonyl, your X is OR when it's an ester, or NR2 when it's an amide. And essentially, you're breaking this bond by adding water across it. And that's what we call it hydrolysis, because you're using water to break apart the molecule. So lysis means break apart, hydro is water. So if we use a good form of a nucleophile, which is hydroxide, that can actually improve that and make that happen quicker. And that's when we would call that base-promoted hydrolysis. So that's like giving water the extra edge, making it a bit more negative by increasing the pH. So using a base instead of water actually makes that hydrolysis happen quicker. And similarly, you can do the opposite with acid. You can acid catalyse hydrolysis of esters and amides. And by that, instead of using hydroxide, you use acid H+ in water. And that will also hydrolyse your esters and amides quicker. So if we go through the base-promoted ester hydrolysis, so this is our base, this is a hydroxide. These electrons with negative charge will attack in an electropositive carbon, and then these electrons will then move on to the oxygen. This gives you this species, which we've already seen before. Now we've got two things. This is what we've just added. So the blue portion is what we've just added, that's the hydroxide. And this is our potential leaving group here. So this is our methoxy. So because it's got a methyl group, it's got an oxygen, we call that a methoxy group. And the next thing that needs to happen for this bond to break, here, is these electrons will come back down and kick that off, like that. And then that gives you, what's left is an acid, carboxylic acid, and then you've got this negatively charged species. So this leaving group can take this proton away from here, and then this can be delocalized like a normal acid. So that would give you this form. So because you've got, if you start off with sodium hydroxide, you end up with the sodium salt of this acid, plus this is methanol. So this is a carboxylate, but if you start off with sodium hydroxide, your sodium would then associate with this, and then you've got an alcohol left over. In this case, it's methanol, because you've got a methyl group here. Are there any questions on that? Okay. So it's very similar for amide hydrolysis. So again, this is ester hydrolysis, and we're just going to amide hydrolysis now. So again, we've got our hydroxide that attacks in the same place. Electrons go up onto the oxygen. And then that gives you this species. So we've got our hydroxide, which we've just added, and this is going to be our leaving group. So this is the nitrogen-containing part of the leaving group. The electrons come back down, kick that off to give you this species. And then what can happen is this will pick up that proton again in a similar fashion, and then the electrons from here can be delocalized across here. This would then give you the carboxylate, so your sodium salt, and then an amine left over. Are there any questions on that? I'm going to go through some practice things in the workshop later on, so there'll be plenty of time to go through those in more detail. So we've gone through base-promoted hydrolysis of esters and amides, but you can also acid catalyse ester hydrolysis and amide hydrolysis in some cases. So we're just going to go through the ester hydrolysis here. And in this case, what happens is when you've got the acid, this can be, these lone pairs on the carbonyl here can pick up that proton. They can use their lone pair to pick that up. And this gives you a protonated species. And when that happens, that then makes this carbon more electrophilic. So when the water then attacks in, these electrons from this bond can then neutralise this charge to give you this neutral species. And the reason why that's favourable is because you've gone from something that's positively charged to something that's neutral, that's happy. So when your water comes in, once it's made that bond, so those electrons here going to this carbon, these are showing formation of a bond between that oxygen and that carbon. So when that happens, you've still got your water here, because oxygen's got three things attached to it, it'll be positively charged. Okay? So the next thing that needs to happen is that one of these protons will leave. So essentially what will happen is you need to switch the site of where these protons are. So you've got a proton here, and for this to become a good leaving group, it can pick up a proton to become a better leaving group. So this proton leaves here, and then another one gets picked up here. So you use the lone pair from this oxygen to pick up another proton, and that gives you this species here. So we've neutralised this one, and we've protonated this one. Now, this then makes this an absolutely excellent leaving group, because once this bond breaks and then goes on to here, you're left with just methanol. It's no longer protonated, and methanol is a very, very stable compound. So what the last stage is, you have the electrons from this oxygen, it could be this one or this one, because they're both they're not the same, but they can both do it, but only one does it. So the electrons from the lone pairs here can be pushed down, and then that kicks that off. And we call that an elimination. But you'll quite often hear medicinal chemists say, pick that group off, well, that's our leaving group, that goes. But what we mean is we're eliminating it. It's going away from the molecule. And then that gives you this molecule, which is basically a protonated acid. This proton can be lost to neutralise that positive charge to give you the acid, carboxylic acid, and then an acid left here. And then this is also, this leaves as just methanol on its own. So the good thing about, this is why it's acid catalysed, not acid promoted, is that you regenerate your proton when you do this type of reaction. So when you do ester hydrolysis, you only need a small amount of acid to actually make that happen very, very readily. So this gets regenerated right back, and it can go. So it's a true catalyst. So you don't need a lot of acid for this to happen, you only need a catalytic amount. Any questions on this? Okay. So different carbonyl groups have different reactivities, and this is dependent on essentially how attractive it is to a water molecule. And the more electropositive that carbon is going to be, the more attractive it's going to be. So if you've got something really electronegative next to it, like acid chloride, the electron is going to be withdrawn really, really nicely away from that carbon. So that carbon, in this situation, it's next to an electronegative oxygen and electronegative chlorine, and actually that's going to have electrons withdrawn that way, which makes that very, very electropositive. So this is the reason why acid chlorides are very, very reactive towards nucleophiles and water in particularly. Similarly, acid anhydride here, because you've already got your carbonyl, but then you've got this species here which can withdraw electrons, because this is very electron withdrawing, because it's got two oxygens, so it's withdrawing from this by the inductive effect again. This also will react very, very readily towards nucleophiles. Then the good thing is with these is that the chloride, if that leaves, is a very good leaving group, and here this species would also be a very good leaving group, because if this bond breaks and it goes on to there, this negative charge can be delocalized over this species here. So this species will be very, very stable. Esters are less reactive than anhydrides, but more reactive than amides, and amides are the least reactive of all of these different types of carbonyl groups. So the reason the amides are less reactive is because the lone pair on the nitrogen can delocalize this way. So although nitrogen is electronegative and it can withdraw electrons by the inductive effect, because it's got its lone pair and it can donate in and then back up there, that means that there are two effects playing off on each other. So you can, so you've got electron donation and also electron withdrawing. And with amides, the electron donation outweighs that, so that resonance makes that less reactive. So in terms of relative rates, the fastest is the acid chloride, because the chloride's a really, really good leaving group, and actually that makes that oxygen, that carbon very, very much positive. So this is relatively fast. So if you have an acid chloride and you add water, you're going to see quite a vigorous reaction even at room temperature. If you have an anhydride and you add water, that's going to react at room temperature, but it'll be slower. Like I wouldn't like if I wanted to quench or stop a acid chloride from reacting any further, and I wanted to put some water in it to stop it doing it, I'd probably want to put that reaction on ice, because it'd probably get quite warm. It's quite a vigorous reaction, happens very quickly. Whereas I wouldn't feel so worried about doing it in there. So I'd probably still put it on ice, but I wouldn't be as concerned about a vigorous reaction. Now, in terms of hydrolyzing with water and ester, this is only really going to happen if you heat it and then you have some sort of catalyst. So either acid or base. And then the same thing with the amide, that you need to heat for a long time to hydrolyze that amide. So these are kind of reflected in the reaction conditions. So if you want to hydrolyze an amide, it's going to take you a lot longer than hydrolyzing an ester. So if you're thinking about making a compound and you need to hydrolyze an amide and you've got an ester present, that ester is going to get broken down long before your amide. So you need to bear in mind the reactivity of these types of different functional groups. So these leaving group ability and reactivity kind of have a relationship with each other, as we've kind of implied before. So these are the different leaving groups. So as I've said, the chloride anion is very, very happy, relatively stable. You're used to seeing it, so it seems quite familiar. The carboxylate, again, is stabilised by resonance. This, what we call this is an alkoxide. So this is like an alcohol, but because it's got the negative charge, we call it an alkoxide. These are less stable, but that makes them actually more reactive. And then the equivalent for the amine, and then the last, and this is the one that really doesn't want to leave on its own at all, would be just the alkyl chain with a negative charge on it. So these are going to be carbons that are negatively charged, and that would be really, really unstable. So as you go up here, the leaving group becomes less stable. Therefore, this is less likely to leave. So these are really stable leaving groups. These are less stable leaving groups. And this is related to the pKa-H. So how easy is it to take a proton off an aliphatic carbon? Very difficult. So the pKa of HCl is very low, so it's very easy to take a proton away from HCl as a gas. It's very easy to take, it's relatively easy to take a proton away from a carboxylic acid. So the pKa of those is about 5, and that's the reason why at physiological pH, which is 7.4, all carboxylic acids are deprotonated, because that proton is so easy to take away that that'll happen at that point. The pKa for alcohols is higher, so it's about 16. So you've got to really kind of take it, you've got to really force something to take that proton away, and that's the reason why this is more difficult as you go up here. So the leaving group is related to the stability of this species, and that's related to how easy it is to take away that proton. So it's kind of related to acids and bases as well, so who will those? So, esters and amides. So, I've already mentioned esters are easier to hydrolyse than amides. Both functional groups contain a lone pair that's in conjugation with this double bond, like this. But the amide group has, so here we've got the electrons, they donate in, and then these electrons from here go up on the oxygen to give you this species. And this is very, very stable, and the amide actually mostly exists in this form. So amides are very stable because of this resonance. Now, the same thing happens with esters, but because oxygen is more electron withdrawing, you get a competing effect. So, whereas amides, this is the predominant form, so you've got these two resonance species. With esters, you do have that can happen, you can get these two species, because oxygen's far more electronegative than nitrogen. You've got inductive withdrawal of electrons as well, competing. And these two effects start to cancel each other out. Because nitrogen is not as electronegative as oxygen, that inductive withdrawal is much less, so you don't see that effect so much. So in amides, this effect is predominant, whereas in esters, you've got two effects that compete with each other, which means then that this is easier to attack, because it's less likely to be in this form, because you've got this inductive withdrawal as well. So it's about having an inductive effect versus a conjugation effect competing with each other. The conjugation always wins, but in this case here, because oxygen is far more electronegative than nitrogen, that's the reason why that's going to have an effect. So you do still see these species, of course, but because oxygen is really electronegative, you will see this does play a role in there. So because there's greater electronegativity on this oxygen, greater electron withdrawal through the inductive effect here, that means that this carbon is more electropositive than this one in the amide. Okay? So that's the reason why esters react quicker than amides. It's this balance between the inductive effect and conjugation. So these groups that are prone to hydrolysis, so we've covered esters and amides. And remember, cyclic esters and amides are still obviously esters and amides as well. So a lactone is a cyclic ester, and a lactam is a cyclic amide, and they're also going to react in a very similar way. And there are examples of different drugs that contain these functional groups. So there's an ester in aspirin, procaine. In amides, you've got paracetamol, is a very, very commonly used drug that's got an amide group in it. Peptides, so the precursors to proteins that make up basically most of your body, they are made through amide bonds. So if amides were easily broken down, we would not be able to exist. So our proteins aren't made up of esters, the majority of the bonds that hold them together are amides. In lactones, so these are cyclic esters, in warfarin or digoxin, which you might have heard of before. And then there's plenty of lactams all over the place, but penicillin is like one of the key compounds that we're probably familiar with that contain ester. Some other groups that are prone to hydrolysis I've just put here, so it's thioesters. So acetyl coenzyme A contains thioester. Phosphates you'll see in DNA and nucleotides, so you should be well into reading your TBL pack by now, and you'll be doing that TBL with Paul, I think next week. Acetals, which are in sugars, and then imines, which are in quite a lot of different drugs as well. So we're just going to go through why hydrolysis is important. And we do hydrolysis in medicinal chemistry, but you actually do quite a bit of hydrolysis in the kinetics of that in pharmaceutics. So it's involved in drug synthesis, so sometimes we use ester and amide functional groups to what we call protect functional groups, so we can actually perform reactions on them. So we use them in drug synthesis. They're critical in drug stability, so the stability of a drug over time and how long it's going to stay in the body will depend on the types of functional groups there are, and also how prone they are to being hydrolyzed. Some of these can be involved in the drug mode of action, and some of them are involved in development of their pharmacokinetic profile, so how long they stay in the body. So something you can do at home is identify the functional groups which will be hydrolyzed under physiological conditions. So prodrugs, you might have heard of prodrugs before, but these are where you have a drug molecule that has what kind of, I would say, a group that's protected, and then in the body that gets broken down and that protection gets removed naturally as part of the metabolism process, and it's that molecule that's the active drug. So you have quite often an inactive drug that goes into the body, and then when it gets broken down, it releases that active drug. That's what a prodrug is. And this is really good because it can actually improve the properties of the drug. So, for example, it might be that sometimes a drug needs to cross the cell membrane, and actually the drug molecule itself will find it very difficult. So by putting a protecting group on there, it will be able to pass the cell membrane, get broken down, and then it can actually perform its action. Sometimes this can prevent drug toxicity by putting a masking group on there. So then once it gets broken down, it's not going to be toxic for as long. These groups can also mask a bad taste for orally bioavailable drugs. And also, sometimes drugs might have a very short duration of action. So they have a very short half-life in the body. If you put a functional group on that gets broken down or metabolized, that means that the duration of action in the body will be longer. So you have longer for that drug to be able to actually work. And most of the time, these prodrugs are usually actually activated by hydrolysis. So one example, is a really notable example of improving distribution of a drug, is the difference between morphine and heroin. So the difference between morphine and heroin in their structure, so you have hydroxyl groups in morphine, and these are essential for their analgesic activity. So what happens is, if you mask these with esters, so having acetyl groups on each of these rather than having the free hydroxyl groups, you convert morphine to diamorphine or diacetylmorphine. So it's called diamorphine, and this is commonly known as heroin. But when you do this, what happens is this makes this drug more lipophilic, and it can actually cross the blood-brain barrier a lot better. And then these get cleaved, so broken down by esterases in the central nervous system, and that allows that drug to then be released. So that's the reason why heroin is much, much more effective than morphine for those different types of properties. Another example could be to increase oral bioavailability. So this drug here is actually a free acid, so you've got your carboxylic acid here, but what you can do is you can have a different version of this that has an ester group instead of an acid. So this group here is a 5-indanyl group, and this makes it a little bit more lipophilic. And then what happens is that's more readily absorbed because it's less polar, and then this gets broken down by esterases, so enzymes that break down esters in the bloodstream to release the active drug. Another example is with salicylic acid. So this is the compound that was originally discovered from willow bark, which is where aspirin's been derived from. So salicylic acid's actually, it has good pain-killing effects, but this phenolic group is pretty bad for your gastrointestinal tract, and it can cause bleeding. So the development of this drug was to mask this phenolic hydroxyl group with an acetyl group, and that then gets hydrolyzed later on. So that's an ester, so it's very easily hydrolyzed, which then gives the free drug. So that drug spends less time being in the more kind of destructive form than it does when it is in the acetyl equivalent. So aspirin has much improved properties in terms of you don't get gastrointestinal bleeding as much as you would do with salicylic acid. And again, it's just the introduction of the ester group that can be rapidly hydrolyzed and then release the active drug. You can actually introduce esters that are very lipophilic. So here we've got a compound that's connected by an ester, and as you can see here, this is CH2 8 times with CH3 on the end. So this is a very, very long aliphatic chain. And these long aliphatic chains actually are very lipophilic, and what can happen is this then will then go into your fat tissue, because that's very, very similar in structure, and then it will get slowly released over time as it's hydrolyzed. So what I've kind of given is a summary of hydrolysis. Hopefully you'll appreciate how common a reaction it is, and amides are less susceptible to hydrolysis. Esters are more likely to be hydrolyzed, and we can use that to our advantage for different applications in pharmacy. Claydon, Greaves, Warren, and if you get the earlier version, Waddle's really, really good book with some extra reading for you there. I'd just like to say it's my last lecture I'm giving, so I will see you guys, and hopefully all of you guys, next year when I'm back for year 2. But good luck with your exams, and if you have any questions, Dr. McDermott will be on hand to help